Section 11.2.10-T. A researcher studies water clarity at the same location in a lake on the same dates during the course of a year and repeats the measurements on the same dates 5 years later. The researcher immerses a weighted disc painted black and white and measures the depth in inches at which it is no longer visible. The collected data is given in the table below, and we're going to complete part A through C. Here's the observations. We have 6 observations. Here's the date. Here's the initial depth. And there is the depth 5 years later. Now in part A it says, why is it important to take the measurements on the same date? Well, a sampling method is dependent when the individuals selected to be in one sample are used to determine the individuals to be in a second sample. Dependent samples are often referred to as matched pair samples. Measurements should be taken on the same date because using the same dates make the second sample dependent on the first and reduces the variability and water clarity attributable to date. Okay, the next question says, does the evidence suggest that the clarity of the lake is improving at the alpha equals 0.05 level of significance? And note that the normal probability plot and a box plot of the data indicate that the differences are approximately normally distributed with no outliers. So it's already telling us that the normal probability plot and the box plot of the data is already indicating that it's approximately normal, so we don't need to check for that. Okay, so let's go ahead and take a look at this information here. Okay, now part A showed that this problem deals with matched pairs, meaning that you have an initial depth and a depth 5 years later. Now it is given that the data were collected by random sampling and that the differences were normally distributed, which is what it's telling us in that second sentence here. Now, a statement is made regarding the mean difference from the matched pairs data. The statement is used to determine the null and the alternative hypothesis. The clarity of the lake is staying the same is the null hypothesis. The clarity of the lake is improving is the alternative hypothesis. Now, the hypothesis can be instructed in one of 3 ways, where the mean of the differences is the population mean difference of the matched pairs data. Here we have a two-tailed, we have a left-tailed, and a right-tailed. Now, if we take a look at the differences, before we look at this next sentence, okay, let's take a look at the differences from x minus y, meaning that if we let d I equal dx minus I, so we're going to look down here, we're going to create another column, d subscript I is going to equal x I minus yi, meaning that is the differences. So we're going to take 34.7 and then subtract 38.2 and we get negative 3.5. Okay, if we take the difference between x and y here, 40.2 minus 48.1 is negative 7.9. 45.3 minus 47.8 gives us negative 2.5. 39.5 minus 48.4 is going to give us negative 8.9. 49.7 minus 51.1 is negative 1.4. And 33.8 minus 37.76 is negative 3.8. Now, the hypothesis test that applies to the matched data is going to be the left-tailed. Because if the alternative hypothesis is true, there will be negative differences. And you can see here that there's negative differences. So recall that this test should be conducted at the alpha equals 0.05 level of significance. Okay, so first, okay, let's determine what is the null and what is the alternative. Okay, we're talking about the mean difference, so we know that the population mean difference is going to be less than 0 since it's a left tail. And we know that the population mean difference for the null is always going to have the equality. Okay, next, we then know that it is going to be a left tail test. And number 3, we know that alpha, or the significance level, is going to be at 0.05. 5. Okay, so now we have that information. The next information is we want to be able to find the test statistic. So if you look here, here's our formula. And so D with an average over that means the mean of the differences. And then S subscript D is the standard deviation of the differences. And then N is going to equal the sample size, which is 6. Okay, so now what we're going to do is we're going to use Statcrunch to determine the mean of the differences and the standard deviation of the differences. So I'm going to go ahead and open up this data in Statcrunch. Okay, and then what I'm going to do is I'm going to go ahead and then title this column as the differences. And I'm going to go ahead and put those values in. So we have negative 3.5, negative 7.9, negative 2.5, negative 8.9, negative 1.4, and negative 3.8. Okay, and so now we're going to go ahead and go to Stat. We're going to go to Summary Stats, and we're going to go select Columns. And the columns we want to find is the differences. So we're going to select differences. We want to find the mean and the standard deviation. So let's go ahead and compute that. Okay, so let me go ahead and copy that. Okay, so here we have our mean and our standard deviation. So let's go ahead and write out the mean here. So let's go ahead and write the mean completely with what we have, which is negative 4.666667. And then our standard deviation is 3.0283109. Okay, now let's go ahead and put this into our formula. So in the numerator, we have negative 4.6666667, and then we're dividing that by the standard deviation of 3.0283109, and then we're dividing that by the square root of 6. So let's go ahead and put that in our calculator. Okay, so in our numerator, we have parentheses negative 4.66667, and then we're going to divide that by parentheses in the numerator. We have standard deviation of 3.0283109, and then dividing that by the square root of 6. Move the arrow to get the parenthesis, and then hit enter. Okay, so here we have our value that we get in our calculator, and then we're going to round this to 2 decimal places, which is going to give us negative 3.77 for the test statistic. Now, if I didn't use, if I rounded this to negative 4.7 and then rounded this to positive 3.03, we're going to get a different decimal. So my suggestion is just to write in the entire number into the formula so that you don't get any minor incorrections when you're plugging in the test statistic. Okay, so now we have our test statistic. So what do we know? Well, we're going to draw a picture. So what does our picture look like? Okay, well, we know that we have a bell curve. So here's our bell curve. And then we have our test statistic. So our test statistic is located here at negative 3.77. And then what we want to do is we want to be able to find the p-value. Okay, so in order to find the p-value, we can either use the table or use what we've done before. We can use the t CDF, since that was what we're looking for, we know that we have the lower bound is negative 9,999. The upper bound is negative 3.77. And recall that whenever we want to use TCDF, we have lower bound, we have upper bound, and then we have the degrees of freedom. So the degrees of freedom is the sample size, which is n minus 1. The sample size is 6 minus 1 is equal to 5. So therefore, this is what we're going to plug into our calculator to find the p-value. So let's go ahead and do that. So here, in order to find the p-value, you hit second and then distribution. Scroll all the way down to TCDF. And then put in negative 9999. So negative 9999 is the lower bound. The upper bound is negative 3.77. We know our degrees of freedom is 5. And then we're going to select paste. And then we're going to go ahead and select enter there. So now we can see what our p-value is going to look like. So therefore, here we have our p-value, which is 0.0065. So we can say that this is equal to 0.0065 for our p-value. Okay, so let's take a look at step number 6 then, because we want to be able to compare. So for step number 6, what we're doing is, it says we're going to compare the p-value to alpha. So let's take the p-value versus the significant level. So we know the p-value is 0.00065, and we know that alpha, the significant level, is 0.05. Okay, so if we compare that, we can see that this is less than. So if the p-value is less than alpha, then we're going to reject the null hypothesis. So therefore, here we are going to reject the null hypothesis. And now we're going to be able to state our conclusion. So the conclusion would then be that there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that the clarity of the lake is improving. Okay, so next, it says draw a box plot of the difference data. Does this visual evidence support the results obtained in part B? Now in part C it says draw a box plot of the difference data. Does this visual evidence support the results obtained in part B? So let's go back to Statcrunch. And in Statcrunch, we take a look at the column where it says differences. And we're going to graph a box plot. So we're going to hit select graph, go all the way down to box plot, select differences, and we're going to make sure that we draw the boxes horizontally. Okay, and then let's mark where the mean is. Okay, so let's go ahead and compute. So therefore, here is our box plot. Okay, so let's take a look at the box plot. Well, if you take a look at the box plot, you can see that all the numbers in the box plot are negative. Here we have -2, -4, -6, -8. So, does this visual evidence support the results obtained in part B? Well, we say yes, because the box plot supports the lake is becoming more clear since most differences are negative.